Yes, thank you. Uh, yeah, let me have it. So I had it a minute ago. As usual, I
Mhm.
struggle to find my presentation
Click
here.
the rectangle.
Can you see my presentation now?
Not now.
Okay, 1 second.
Not now. No.
Okay.
Not presentation.
Um,
Uh-huh.
is that better?
Very good. Please start.
Okay. Okay. You see my presentation now. Is that correct?
Very good.
Okay, excellent. So thank you very much for the invitation to attend this seminar. I've been aware of the Kharkiv seminar for many years, and I've always hoped to be able to attend. So I'm pleased to be able to attend today. Uh, why am I talking about the GUM methodologies and so on? Well, uncertainty quantification is playing a bigger role in scientific endeavor. People are now aware that we need to be able to evaluate uncertainty. And we are hoping that the role of metrology can help the general scientific community in evaluating and working with measurement uncertainty. And we've been doing so with the GUM for many years. And in particular, if we want to develop new measurement modalities such as imaging, using machine learning, and so on, we need to develop the uncertainty quantification methodologies that go with it. And by providing uncertainty quantification, we are supporting trust, interoperability, and interpretability, so a framework of metrology traceability. So this is why metrology is important to scientific uh, endeavors, because we're able to provide trust and so on. So people are very interested in uncertainty quantification, but my issue is what are we, what is the thing that we're trying to quantify the uncertainty of, and how is it quantified? And people are looking to the GUM and GUM documents to provide guidance to help them with their uncertainty quantification. But my issue is that the GUM methodologies are not all the same. So I'm in my head there are four sort of GUM methodologies. The first is the GUM LPU, which is based on the law of propagation of uncertainty. So propagation of first and second moments as means and variances to an input-output model. And that's been used for hundreds of years. You see, we can also talk about propagating higher moments, in particular kurtosis. And Professor Sakharov has written some very interesting papers on that issue. Then the next GUM methodology is the propagation of distributions through an input-output model, where we assign distributions to the input parameters and propagate those and sample from those distributions and propagate those samples through the input-output model. So both the GUM and LPU and Monte Carlo approach are using the same input-output model. The GUM Welsh Satterthwaite formula and coverage intervals is significantly different in my head from the LPU and Monte Carlo approach. And then there's the GUM Bayesian inference. Now there isn't a GUM Bayes, but many people have looked at using Bayesian inference applied to measurement uncertainty evaluation and contrasting and comparing with, in particular, the GUM Monte Carlo approach. So I want to say something about all four of these methodologies. And underlying these methodologies, there are sort of two sides of to look at. There's at the highest level there are forward problems and there are inverse problems. The measurement equation is a forward problem approach to looking at things. The observation equation approach is an inverse problem. There's parameter estimation, which is a forward type estimation. There's Bayesian inference, which is an inverse type inference. There are sampling distributions, which are forward type concept, state of knowledge distributions, which is an inverse type concept. And corresponding to that, there's a sort of classical confidence intervals and Bayesian coverage intervals. So these are the underlying concepts that are floating around with these four GUM methodologies. Now, what I'm going to talk about today is based on the simplest measurement scenario you can have, where you're just measuring a single quantity, repeated measurements. So you're generating observations Y, Y1 through Ym, and the model is that they're drawn from a Gaussian distribution centered at A with variance sigma squared. Okay, so the standard model for repeated measurements with Gaussian sampling. We know that if we can calculate the mean of the sample and the variance of the sample using these formula. And in classical inference, we say that A, the parameter of interest, the thing we're trying to measure, is estimated by the sample mean, and the variance is estimated by the sample variance. Okay, so that's straightforward and well known. We have sampling distributions. So here's an example of the sampling distributions as opposed to state of knowledge distributions. We've got sampling distributions for the estimate. The estimate A hat, which is the average of Gaussian variates, is also Gaussian. The sampling distribution for the sample variance is a gamma distribution or a chi-squared distribution. And putting those two together, if we let Z be the difference between the sample estimate, A hat and A, divided by the sample standard deviation, we know that Z is distributed as a T distribution with new degrees of freedom. And the fact that Z is a sample from this T distribution allows us to calculate coverage intervals. Now, we never know Z because we never know A. A is what we're trying to measure, but we do know information about Z, and we use that to assign a coverage interval. So classical inference doesn't say anything about state of knowledge distributions and the like. Classical inference says, I've got a methodology that will deliver a confidence interval, and this confidence interval will contain the true value of the measurement 95% of the time, for instance. The Bayesian approach requires us to assign prior distributions, but we can do so in a way that's non-informative. And on the basis of those prior distributions and applying Bayes' theorem, we get a posterior distribution for the things of interest, A and sigma squared. And we can factor this posterior distributions with a posterior distribution for A, given sigma squared, and that is a Gaussian distribution. And we've got a factor which is sigma squared given Y, which is an inverse gamma distribution. And when you stick those two together and integrate out the dependence on sigma squared, we end up with a T distribution, a state of knowledge distribution for A. And then at this point, I point out that A hat, the estimate, is not a sample from a t distribution. A hat is a sample from a Gaussian distribution. And we'll need that difference later. And in this case, the Bayesian 95% coverage interval based on a t distribution is the same as a classical confidence interval, but they have different interpretations. The Bayesian coverage interval says that my artifact is a member of a population, 95% of which have values in this interval. So you're saying something directly about the artifact that's being measured. Now let's generalize this simple model to the next simple model where we're measuring two quantities, each using repeated measurements, each governed by a Gaussian distribution. So we're sampling repeated measurements from two Gaussian distributions involving two means, A sub k, involving two standard deviations, two variances, sigma squared sub k. So we can look at each experiment independently. We get estimates A hat sub k and S squared sub k for the mean and variance. What we're requiring to say something about the sum of those two quantities. So you can imagine measuring two masses or measuring two gauge blocks that we stick together, ring together, and we want to know the combined mass. We want to know the combined length. In the classical approach, we know that the standard, the estimate, A hat, which is the sum of the estimates of each of the quantities, is a draw from a Gaussian distribution. And if we could show that the sampling distribution for S squared, which is the sum here of the sample variances, if we could show that that was a sample from a gamma distribution, then we can go through exactly the same mechanism as we've done for a single quantity and deliver this Z, the statement that this Z is a sample from a Gaussian a sample from a t distribution, and on that basis generate confidence intervals for the combined length. So we can use the same approach. That will hold if the sampling distribution for S squared is a gamma distribution. Well, it turns out that the sampling distribution to a sum of gamma distributions, gamma variance, is in fact close to a gamma distribution, and sometimes it's exactly a gamma distribution. Given that we've got S sub 1 squared and S sub 2 squared are gamma variates, we can calculate their mean and variance. Gamma distributions always have a mean and variance. If we want S squared to have a gamma distribution, then we can say, okay, let's find a gamma distribution that is the same mean and variance as that derived from S sub 1 squared and S sub 2 squared. And when we do this moment matching, we end up with a Welch-Satterthwaite formula, which tells us what the t distribution will be, what degrees of freedom it will have. So that's how the Welch-Satterthwaite formula arises. But it does make the assumption, the Welch-Satterthwaite formula applies if we know the sample variances. We don't know the sample variances. Well, we do know the underlying variances. We do know the sample variances, but we assume that the population variances are, in fact, can be approximated well by the sample variances. So making that assumption, this is where we get our degrees of freedom. So this is the one sort of approximation, significant approximation that Welch-Satterthwaite formula makes, but it tends to be fairly benign. It tends to work very well. when we apply a GUM or a GUM MCM approach, we say, okay, our state of knowledge for each of the parameters, A sub k, is a t distribution. We can propagate the means and variances of these t distributions if they have means and variances. In order for them to have a variance, in fact, the number of repeat measurements has to be at least 4. But if we have at least 4 repeat measurements, then we can calculate the mean and variances of each of the summed distributions. We can calculate the mean and variance of the distribution associated with the sum. A GUM LPU will assign a Gaussian distribution to that. The Monte Carlo method will sample from these t distributions and generate a sample for the distribution associated with the sum. The Bayes approach delivers, again, we've got prior distributions associated with the various parameters. But the Bayesian approach will deliver a posterior distribution for the sum A and the sigma squared associated with the sum. And we can factor that, again, as a Gaussian times another distribution, a posterior distribution for sigma squared given the 2 sets of measurements. The posterior distribution for sigma squared is given by the convolution. It's a sum of 2 inverse gamma variates. So it's given by the convolution of 2 inverse gamma variates. And what we have now is that the convolution of 2 inverse gamma distributions is very much isn't a gamma distribution, doesn't look like an inverse gamma distribution. If it did, then the Bayesian posterior would be for A would be a t distribution, okay, and would be in the same sort of world as we are when we just got one artifact, one set of repeated measurements. But in fact, when we've got 2, this convolution of inverse gamma distributions isn't a gamma distribution, means that the Bayesian posterior distribution isn't a t distribution, which means that the Bayesian approach and the well-satisfied approach are significantly different. And these are the sort of coverage intervals we get with the different GUM methodologies for the case where we've got 4 repeated measurements. Arbitrarily, we have the estimates are 0 and all the standard deviations are 1. Okay, and we find that the MCM approach gives us coverage intervals, confidence intervals that are much larger than that given by the well-satisfied approach. The GUM approach, where we assign a normal to the output distribution, is very similar to the Monte Carlo approach, quite close. But the well-satisfied is significantly different. So we're talking about a coverage interval of plus or minus 1.7 for well-satisfied compared to about 2.4 for the GUM. So if somebody's writing a calibration certificate for this measure, and the sum of these 2 masses is sum of the length of these 2 gauge blocks, you know, there's a big range of, you know, what calibration, what interval are they going to use? Are they going to use well-satisfied, which is the GUM one? Or are they going to use a Monte Carlo one, which is GUM supplement 1? So, you know, they're quite different. If we see a calibration certificate with a coverage interval, how we interpret it does it come from a application of well-satisfied, or is it something else? So these are the sort of issues that I think the metrology community need to look at. My next sort of topic relates to the analysis of least squares, analysis of interlaboratory comparison data, which normally starts as a nice paper with Morris Cox on analysis of such data using least squares methods or weighted least squares methods. If, and in this case, we've got a single artifact, but we're measuring it using different instruments, each with its own standard deviation, each with its own variance. If those measurements are drawn from Gaussian distributions centered at the measurand, but with variance u sub j squared, we compute the least squares estimate, we can compute the variance associated with the least squares estimate, and we can assign a Gaussian distribution to the least squares estimate. And in a Bayesian world, the posterior distribution is also given by a Gaussian distribution. That's assuming that all the measurements are drawn from a Gaussian with known variances. I'm interested in the case where, in fact, all the laboratories have been measuring this artifact using different instruments, but they've been asked to measure it with 5 repeat measurements and estimate or provide information about the artifact on the basis of these repeat measurements. So it's instead of having 2 repeat measurements, I've now got more, 8, say, in this case. The Bayesian approach can be implemented fairly straightforwardly. Each laboratory provides a state of knowledge distribution, which is a t distribution. Then the joint posterior distribution for all the parameters can be written down, and we can analytically marginalize all the variances, sigma sub j squared out, and we end up with a posterior distribution for the measurand A, and this is a product of t distributions. So the Bayesian approach assigns to the measurand a product of t distributions. We can apply a least squares analysis where we think of where we recognize that each laboratory is giving us a state of knowledge distribution, which is a t distribution for the measurand, and we want to use this information in a least squares analysis. So what we can say, now least squares analysis assumes that each measurement is a draw from a distribution centered on the measurand. I've already said that the t distribution A hat isn't a draw from a t distribution, but if we assert that it is, if we assume that it is, then we can go through the least squares analysis. We know that the variance associated with the t distribution, therefore we can do a weighted least squares estimate and assign a Gaussian distribution. Similarly, if we say that we can apply a propagation of distributions approach, again we're asserting that A hat is a draw from a t distribution. The least squares estimate is a combination of t variates. We use a Monte Carlo approach to sample from these t distributions, evaluate the sum of these samples in the right way, and what we end up with that the Monte Carlo approach delivers a convolution of t distributions, whereas the Bayesian was a product of t distribution. The Monte Carlo approach is a convolution, different thing altogether. We can also apply Welsh Satterthwaite to this problem, where we think of the measurand or the estimate A hat is being given as a sum of variates, each of which is associated with a Gaussian with a t distribution. We do exactly the same thing as we did in the case of two measurands, we can do it exactly the same for any number. Well, status weight does provide that gamma approximate to the sampling distribution associated with the estimate. We can calculate this Z quotient thing. It will have be associated with a t distribution, and then we can generate a confidence interval for the measurand, the estimate, the least squares estimate. If Cj, the weighting is fixed a priori, then well-stated weight will indeed give you a confidence interval that will contain the true result 95% of the time. But the problem with this, and applying it in this case, is that the weights C sub j depend on the sampled the sample standard deviations. So if we resample that, we get new sample deviations, and we get a new weighting, and that means that well-stated weight does not apply in this case. If we just take a straightforward mean, average withdrawal estimates, then we can apply well-stated weight. And this is the sort of posterior distributions, or the distributions associated with that ILC data we had before. We've got the GUM, the LPU, and approach all centered in the same estimate, but with different distributions. The Bayesian posterior, which is a product of t distributions, is significantly different. Okay, so in this, it's significantly different, and it's significantly different for a good reason. So, in summary, one of the things that I think the metrology community is trying to address is the fact that these GUM methodologies correspond to different implicit models. We must make sure that we never confuse a state of knowledge distribution with a sampling distribution, and vice versa. Well-stated weight is not consistent with the LPU, and it's not consistent with the Monte Carlo approach, and it's not consistent with Bayes, because it's doing something different. It's providing confidence intervals rather than confidence intervals. And, we've got all these different methodologies. If we don't know what methodologies, what models are being applied, I don't think it's straightforward to understand what an uncertainty statement is actually saying. And in the case of ILC data, where we've got repeated measurements, none of the conditions that allow you to apply a weighted least squares approach apply, and you can't apply a well-stated weight approach either. So there's some of the fundamental calculations associated with metrology, are being done on the basis of models that are not totally appropriate. Well-stated weight is quite a bit different from the other approaches. So we only use well-stated weight because we have to deal with the problem of what happens when we've got less than 4 repeat measurements. So there are alternatives. Basically, one alternative is to do everything using Bayesian approaches, which is fine. Although some people don't particularly like that solution. Cox and O'Hagan and Postle and Bonner have looked at other approaches where you're looking at medians and quantiles and so on, rather than means and standard deviations as a sort of summary of a distribution. So thank you very much. I'm sorry I've run over your time, but thank you very much for your attention. And again, thank you very much for the invitation to take part.
Thank you very much, Alistair, for interesting presentation. Dear colleagues, do you have any question to Alistair? Jacek? Your microphone is off.
Yes, of course, but I think about all information. I would like to ask Professor Alistair, the estimator for least square method, it's like Gaussian Markov estimator, is the minimum of weighted least square method. But if you have tried to fit the line to the measurement points with uncertainties of two coordinates. Is it possible the same consideration appropriately applied to as the same way as you do?
Yes. So the case of fitting models to data.
If we have a two-dimensional case.
Yeah, certainly. Yeah, the same underlying considerations applies. Are you doing estimation or are you doing inference? If you're doing least squares estimation, what's the sampling distribution for a least squares estimate? How can you use that for making inferences about the parameters involved, the straight line parameters? Now, the interesting case, which I haven't looked at, is supposing you're doing straight line calibration where you have repeated measurements associated with the X and repeated measurements associated with the Y. So you've got t distributions associated with those pieces of data. How that works through for the whole analysis, I haven't looked at that, but that would be a very interesting thing to look at and be interesting to see.
It's more complicated model, yes.
Yeah. But the same, all these issues to do with whether or not you're doing a forward problem or an inverse problem, whether or not you're doing inference or estimation, these are all the sort of things that we need to consider, and we also need to be clear about when we're describing what we're doing and describing the results of our analysis. That's a message I would want to say.
Thank you.
Thank you again.
Do you have any question?
I have a question on some information to Alistair. Here's Zygmunt Warszaw talking.
Hi, Zygmunt.
Alistair, I find some people in Poland which are interested in organize AMCTM seminar in next years. We can talk about that separately. I give you this information.
Yeah, very, very happy to do that and to see you and Jacek again in Poland.
Thank you.
Any question? Alistair, I have question. Next question. Do you know that the formula, Well-Satterthwaite formula, given in GAM, don't work when we have a correlation between input quantities?
I haven't looked at that, and I can imagine that it wouldn't work. Yeah. There might be something else as an alternative that takes into account the correlation.
Yes. Next question. Do you know that main disadvantage of GAM is independence, the estimates of expanded uncertainty from the PDF of input quantities? Yes? Difference? Yeah. And we have some difference between estimates obtained with GAM and with Monte Carlo method.
Yes, indeed. So there are differences between the GAM LPU and the GAM Monte Carlo method, but that's is calculating something different. It's calculating a confidence interval rather than a coverage interval. they're never going to be the same, or hardly ever going to be the same. And there's no sense in which you can say we can use the Monte Carlo method to validate the wealth settle rate approach, because they're doing two different calculations. That would be what I would want to emphasize.
Thank you. Thank you. Dear colleagues, do you have any question to Alistair? Alistair, thank you very much for your interesting presentation and your answer to the question.
My pleasure. Thank you very much again for the invitation, and looking forward to the rest of the meeting.
Thank you. Thank you. Так, our next speaker is Dr. Viktor Witkowski, but we have not Viktor. And maybe now we go to the next speaker.